Okay, so this is going to be the last of our review videos for Math 1560 Calc 1 at U of L. We'll be putting new videos up sometime next week probably, where we get into the actual calculus material. We'll be starting off with limits next week. So we'll be getting some limit videos up as soon as I have a chance to record them. Now, let's go through the review, finish this off, and we've got to talk about some other trig functions. So we've defined sine and cosine. We've defined them in terms of the unit circle. After sine and cosine, the next most important trig function is the tan function. Okay. Now, notice one thing you might want to keep in mind here. Remember that sine is like the y-coordinate on the unit circle. Cosine is like the x-coordinate on the unit circle. So it's y over x. So this is kind of like slope. All right. When you draw your unit circle and you mark a point on the unit circle and you have this angle theta, if you want to know the slope of this line segment here from the origin to this point on the circle, the slope of that line segment is given by the tangent function. Okay, and so the tan function certainly comes up quite a bit in applications. Then there are the three reciprocal functions: the secant function, which is the reciprocal of the cosine function; the cosecant, which is the reciprocal of sine; and the cotangent, which is the reciprocal of the tangent function. These will come up from time to time. Once we get into derivatives integration, you'll see these guys popping up here and there, and they do have their uses in calculus, but they don't show up too often in practical applications. Sine, cos, and tan are the ones that kind of, get the majority of the work. The other three are kind of along for the ride. One thing to kind of warn you about, and we're not going to talk about inverse trig functions in the review, but we will be talking about inverse functions later. So these are not the same thing as the inverse trig functions, right? So secant, cosecant, cotangent, these are not the inverses of sine, cos, and tan, they're reciprocals. We will be talking about inverses later on though, and I just thought I would mention that because occasionally people get the two mixed up. Now, moving right along, we want to talk about a few of the kind of basic identities that are really key to working with trig functions. You won't need a huge number of trig identities in Math 1560, but occasionally they do come up. And so it's good to know some of the basics. So of course we have the most famous one, this Pythagorean identity, coming from the fact that sine and cos are points on the unit circle, coordinates of a point on the unit circle. And you can involve the other functions if you want. So if you take that equation and you divide the whole thing by cos squared theta, then you get this variant here. If you divide the whole thing by sine squared theta, you get this one. These do pop up from time to time and they do come in handy, so it's good to make sure that you have those in your back pocket. The other identities that take a little bit of work to come up with, and that's why I say these are the essential ones, the ones that you can't just kind of derive on your own without a lot of work, are the addition and the subtraction formulas. So how do you deal with cosine of the sum of two angles, or the difference sine of a sum or a difference? Well, you need these identities here, right? And again, they look a little bit intimidating at first, but as you use them repeatedly, eventually they just sink in and you use them without even thinking about it. There are also the so-called even-odd identities. You can get these from the addition and subtraction formulas, but it's kind of good to keep these in mind anyway. These have to do with the symmetry of these functions when you think in terms of the graph. So the cosine function is symmetric when you reflect across the y-axis. So values for negative x have the same y values as for the corresponding positive x. For sine and cosine, when you jump across the y-axis, the graph flips over. You see this minus sign there. They're examples of what are called odd functions. And so the reason I'm listing these as essential is it turns out that basically every other identity that you could possibly need in a calculus course can be derived from the identities that you see on this page. They cover pretty much everything that you need to know. And There are a few, you don't want to always derive everything from scratch. There are a few that are kind of handy to kind of, have in mind as you go through. Um, Here are a few of the ones that come in handy more often than you might think. The double angle formulas, they come up quite a bit. They pop up all over the place, especially once you get into integration. So this is, how do you deal with cosine of twice an angle, or sine of twice an angle? And by the way, the reason I say that these are kind of derivative, they can be derived for the other ones, because 2 theta, of course, 2 theta is just theta plus theta. And so if you go back and you set x and y both equal to theta in the addition formula I gave you on the previous slide, then you say, well, this is cos theta times cos theta minus sine theta times sine theta. And of course that gives you the cos squared theta minus sine squared theta. If you use the fact that sine squared plus cos squared equals 1, you can also rewrite this in a couple of ways. If you write sine squared as 1 minus cos squared, you can write this as 2 cos squared theta minus 1. If you write cos squared as 1 minus sine squared, you can also get 1 minus 2 sine squared theta. Those are all equivalent identities. And then the one for sine can be obtained similarly. And one of the good reasons to maybe point this out now is, notice that with sine and cos, if you are dealing with double an angle, 2 times theta, this is not simply a matter of pulling out the 2. Okay, you can't bring that constant outside the sine function or the cosine function. That 2 is stuck inside, right? Sine of 2 theta is not just 2 times sine theta, it's 2 times sine theta times cos theta. It's much more complicated. So it's always important to keep these in mind, because again, these are mistakes that people can make when they're being careless. Now, if you play around with this the double angle formula for cosine, you can rearrange things and work out values for when you want to calculate cosine of half an angle. So cosine of, say, pi over 2, or sorry, cosine of theta over 2, sine of theta over 2 are given by these square roots. There is a plus minus out front. The way you deal with that plus minus is by simply being aware of what quadrant you're in. So here's, a very basic example of where you might try to figure something like use these to do something. Let's say you want to calculate, here's an example. Cosine of pi over 12, right? Let's say you want to know what this is. You guys have calculators, you can work these things out, you can figure them out, but there was a time not that long ago where people did not have pocket calculators that could work these things out. People had to figure these things out by hand. People that, even going back maybe 50 years ago, people used to, that were taking a course like calculus, they'd have to walk around with these giant books full of tables of values for sine and cos and logs and things. You don't need those anymore. You can use your calculator, but sometimes it's good to be able to figure these things out. So there are 2 things I could do with something like this. There's 2 approaches I could take. Here's plan A. Plan A is, notice that pi over 12 can be written as pi over 3 minus pi over 4. I'll let you guys confirm that on your own. It's a good opportunity to practice your fractions. The other thing you might notice is that I could write pi over 12 as 1/2 of pi over 6. Both observations are useful because I know values of sine and cosine at pi over 3 and pi over 4 and pi over 6. I know these values. So I could, for example, say go with plan A and say, well, this is using the angle subtraction formula for cos. This is cos pi over 3 cos pi over 4 plus sine pi over 3 sine pi over 4, and then kind of plug things in. So 1/2 times 1 over root 2 plus root 3 over 2 times 1 over root 2, and I would have a value. I'll let you guys try plan B. You could also use this this half angle formula with theta equal to pi over 6, and that would give you another way of also working out a value for cos of pi over 12. What's interesting is you'll get two completely different looking expressions for cosine of pi over 12, but feel free to verify in a calculator that this number here is exactly the same as what you would get. So if I did this with theta equal to pi over 6, I would get the square root of 1 plus root 3 over 2 over 2, and then the square root of that whole thing. That number, believe it or not, is the same thing as this number down here. They look very different, but they do have the same value. All right. That's it for the review portion of the course. I hope that some of these have been useful for you guys. We'll be continuing with videos next week on the calculus material. We'll be starting with limits, then derivatives, and we'll get eventually to integration. Everything you need will be up on these videos. Do your best if you have time to watch them before you get to class, and then you'll be ready to work with us on the problems that we're doing in the classroom.